This video will cover random forests in R. By the end of this video, you should understand how you train a random forest model in R, what factors you should take into account when choosing a model formula for a random forest, what the appropriate number of trees for a random forest model might be, and how we can evaluate random forest models using cross-validation. The R code used in this video is available in the Learning Management System. You'll need the data file dcelectricity.rds if you'd like to follow along. In this video, we're going to train and evaluate random forest models in R. If you haven't already, install the random forest package. Also, let's load the dcelectricity.rds data file and divide it into training and test samples using the sample function. Looking at my R code, I'm going to load several libraries here, including the random forest library and model R. After that, I load the dcelectricity.rds data file. I'll divide it into training and test data using the sample function. I'll just run all of that now. Before we get started training models, I'd like to make a quick note about the examples in this video. You should be familiar with the dcelectricity.rds data file by this point. We're going to continue using it for consistency and ease of use. This will give you good exposure to the mechanics of how you'll actually train random forests. I really want to emphasize that this data file is not really a setting where random forests shine. There's only a few observations, and there's only 2 features in the data file. Random forests are best with large data sets and many relevant features. These large data sets increase training time substantially, particularly as you add more features and observations. So while the dcelectricity.rds data file is a good data file to get started with, it's really not going to show you how well random forests perform in the real world. There are many packages for performing random forest estimation in R. There's the random forest package, XGBoost, which adds boosted regression trees, Ranger, GRF, which adds generalized random forests and honest trees, and many others. In this class, we're going to use random forest. It has a modern syntax, it's very flexible, and it's fast-ish. There are other faster packages that are harder to use, and possibly some slightly more modern packages that aren't as flexible. I think random forest is a good compromise. You're going to train random forest models with the random forest function. The most basic model training is very similar to modeling tools we've already used. You'll use the random forest function, you'll provide a formula, and then you'll provide a data equals argument with your training data. The formula is a model formula with a label, a tilde, and features separated by plus signs. So let's get started training random forest models. We're going to define 2 formulae. Formula A is just going to be demand as a function of 2 features, high temp and low temp. Formula B will look very much like what we've trained OLS and lasso models in the past, with demand as a function of higher order polynomials of high temperature and low temperature, and their 2-way interactions. We'll train OLS models for both of these formulae. We're only going to train a random forest model for Formula A. Why is that? Remember that random forests don't place an underlying functional form assumption on the relationship between the features and the label. This means that you don't need to use polynomial or interaction terms in your formula. And in fact, including polynomial terms in your formula with a random forest will generate an error. After we train these models, we're going to compute predictions from each of them on our test data, and then compute the out-of-sample root mean square error. Looking at my R code, you can see first I define Formula A and Formula B. I'm then going to train OLS models for each of those formulae. Then I'll train a random forest model on Formula A. After that, I'm going to generate predictions for each of these models using the predict function, and then I'll summarize those predictions to compute the root mean square error for each of these models. Remember, root mean square error is the square root of the average of the squared prediction error. Let's run all of that and see what the root mean square error from each of these models looks like. You can see the simple OLS model with only 2 features has a root mean square error of 317,878. The more complicated model with higher order polynomial terms in their interactions has a root mean square error of 212,773. And the random forest model with only those 2 features has a root mean square error of 190,765. We're evaluating these models out of sample. So in general, from this evidence here, we'd prefer the random forest model for its substantially lower out-of-sample prediction error than either of those OLS models. Now that we've created predictions for these models, what I'd like to do is visualize them. I'm going to create a visualization with OLS predictions from Formula B on the x-axis against the actual value on the y-axis. I'll do the same thing with that random forest model. I'll also add a slope 1, intercept 0 line that would denote perfect predictions. Looking at my R code here, you can see I have the ggplot code for that visualization. Demand is always going to be on the y-axis, so I'll make that part of the ggplot aesthetics. I'll then add a point layer with the OLS predictions on the x-axis, another point layer with the random forest predictions on the x-axis, and then finally that slope 1, intercept 0 line in black. Let's run that and take a look at the visualization. The OLS dots are red and the random forest dots are blue. You can see they both generally follow the 45-degree line, with the exception of a couple of large prediction errors from the OLS model, here and here. Remember that random forests generate predictions as the average value of the label in each leaf, so they're very unlikely to produce large prediction errors. This is one of the reasons that random forest models perform so well predicting out of sample. You might remember from a previous video that random forests can be based on many hyperparameters. These can be adjusted as part of the arguments to the random forest function. I've shown a few of them here, along with their default values. First, and probably most important, is the number of trees. The default value in random forest is 500. You can change that using the nTree parameter. The mTry parameter defines the number of features that random forest is going to try at each split. This by default is the number of features you provided to the model divided by 3. Next is the node size. This is the minimum number of observations that can be in any leaf. The default is 5. Lastly is the maximum number of nodes, max nodes. By default, random forest is going to grow trees until it can't split any more leaves without going below the node size value. If you set max nodes to a number less than infinity, it might limit the size of the tree based on the number of leaves. There are many more parameters you can adjust as well. In the examples that I show in this video, none of these parameters make much difference, but in practice they can be very important. Most important among these is the number of trees. By default, random forest grows 500 trees. This is almost certainly not enough for reliable forecasting in any context. More trees means more precise forecasts. You should generally grow at least thousands of trees if you're trying to use random forest for forecasting. And importantly, the number of trees that you need for reliable forecasts increases as the number of features in your model grows. As a general practice, people will usually explore and cross-validate random forest models with fewer trees, but when they're ready to make final models that they'll use to be generating forecasts, they'll add many, many more trees. As an example of this, I'd like to train a random forest model using Formula A with 5,000 trees. We'll add predictions to our test data, and then compute the out-of-sample root mean square error for both the original random forest model with the default of 500 trees and this new model that has 5,000. And then we'll ask ourselves if the results changed. So taking a look at my R code, I'll train a new random forest model, this time using 5,000 trees. After that, I'll add predictions to my test data from this model. I'll compute the root mean square error for both my original model with 500 trees and this new model with 5,000 using the RMSE function. Let's run all that and take a look. You can see the root mean square error from these models are very, very similar, but the root mean square error from the model with more trees is slightly higher. I'd like to see how well the predictions from these two models correlate. So let's go back to my code. I have here some ggplot code. I'm going to create a scatter plot with predictions from the model with 500 trees on the x-axis and predictions from the model with 5,000 trees on the y-axis. If these models are making very similar predictions, they should all fall along a slope 1, intercept 0 line. So I'll draw that line in as well. Let's run that and take a look at the visualization. Looking at the visualization, you can see most of the dots here fall almost exactly on that black line. The models are generating very similar predictions to each other. This is what we'd expect when we're training random forest models on datasets as small as the dcelectricity.rds data file that only has a few hundred observations and 2 features. As you add more features and add more data, you can expect the number of trees to make a substantial difference in what your predictions look like. Again, more trees is always better. Just like OLS models, we can cross-validate random forest models using cross-v k-fold. The process works exactly the same. We'd use the cross-v k-fold function to create validation data. We'd then train models and save the results using the map function and our modeling tool here, random forest. We could then compute the out-of-sample loss on the test data, again using the map2double function and the root mean square error function from the model R library. This would give us a tibble with 10 values of the root mean square error, 1 for each cross-validation fold. We can compute the average across all of those using the summarize function. So I'd like to use cross-validation to train and compute an average out-of-sample root mean square error for both a random forest model using Formula A and an OLS model using Formula B. After that, we'll take a look and see which model we prefer. Looking at my R code, you can see I follow that exact template here. I'm going to take my full electricity data, I'll feed it to the cross-v k-fold function and create a cross-validation tibble with 10 folds. I'll then train both OLS and random forest models using the training data, and then I'll compute the root mean square error on the test data, and finally take the average of each cross-validation iteration using the summarize verb. Let's run all of that and look at the output. You can see here, the root mean square error from the OLS model is a little bit less than the root mean square error from the random forest model. This isn't what we found before with our out-of-sample evaluation. And this can really show you the value of cross-validation. We spent some time in previous videos working through OLS models and choosing the model that was used in this video for Formula B. It is the model that generated the best out-of-sample forecasts using OLS. So it's not surprising on this small data set that only has 2 underlying features that we could find an OLS model that performs a little bit better than random forests. When you start to get in the wider world of larger data sets with many features, this usually won't be the case, and random forest models will usually outperform their OLS counterparts.